Precision Measurement for Machinists, a MasterTask multimedia program. Lesson 4, Using the Inch and Metric Systems. When parts are being produced in the machine tool industry, there must be a standardized system in place that allows the machinist to know if he has produced an acceptable part. This is called a measurement system. The two measurement systems used in the machine tool industry are the inch system and the metric system. In many machine shops today, both measurement systems are utilized, and understanding their differences as well as how they relate to one another is an important skill for the modern machinist. There will be 5 parts to this lesson. Part 1 will explain the principles of metric measurement, while Part 2 covers the principles of inch measurement. Part 3 explains common errors in performing and expressing calculations and how to avoid them. Factors that affect measurement are described in Part 4, and Part 5 introduces the steel rule. Part 1. The principles of metric measurement. In order to work with metric dimensions, you must be able to read normal print notation in millimeters. 28 millimeters on this print is written as 28.0. The decimal point indicates that all numbers to the left of the decimal are whole millimeters. Numbers to the right of the decimal represent values smaller than 1 whole millimeter. The first digit to the right of the decimal will count the number of tenths of a millimeter. In this example, the 0 indicates the number of tenths. Also notice the tolerance of plus or minus 5/10ths of a millimeter. The second place value represents the number of hundredths of a millimeter. When measuring to very close tolerances, the value will be measured to the thousandth of a millimeter, 3 places to the right of the decimal. A thousandth of a millimeter is also called a micron. In order for you to be able to identify approximate dimensions on workpieces using the metric system, it is a good idea to be aware of the following inch-metric conversions. In an earlier lesson, you learned 2.54 centimeters equals 1 inch. Moving the decimal of 2.54 centimeters 1 place to the right will give you the measurement in millimeters, 25.4. Therefore, 1 inch is approximately 2.5 centimeters or 25 millimeters. 100 thousandths of an inch is approximately 2.5 millimeters. 6 inches is approximately 150 millimeters. And 12 inches is approximately 300 millimeters. Now look at this metric steel rule. This rule is graduated to 1 millimeter. Note that the graduation labeled 10 millimeters is the equivalent of 1 centimeter. You will learn more about the steel rule later in this lesson. Part 2. The principles of inch measurement. Dimensions measured using the inch system can be recorded 2 different ways. They can be written as decimals, such as thousandths of an inch, or they can be written as fractions. When using decimals, the inch is divided into 1,000 equal parts, and when fractions are used, the inch can be divided into several different fractions. In our current example, the inch is divided into 64 equal parts. Decimals are used when manufacturing and measuring precision machine parts, and fractions are typically used for standard stock sizes, thread sizes, and cutting tool sizes. Typically, the smallest graduation of a steel rule is 6/4 of an inch, while the more precise calipers and micrometers are graduated to thousandths of an inch. The key fractions of an inch for measurement purposes are the half, the quarter, the eighth, the 16th, the 32nd, and the 64th. These fractions are based on a factor of 2. 1/64 times 2 is 1/32. 1/32 times 2 is 1/16, and so on, all the way to 1/2. When expressing inches using decimal numbers, measurements smaller than 1 inch work like the metric system. The thousandth is based on a factor of 10, just like the metric system. So converting measurements from tenths to hundredths to thousandths of an inch is done quite easily. 1/10 of an inch is equal to 100 thousandths, and 1/100th of an inch is equal to 10 thousandths. Thousandths can be written as fractions. Here you can see that the fractional equivalent of 1,000th is 1 over 1,000. You can also see that 64ths do not evenly convert to thousandths. Many measuring devices, such as this micrometer, have a conversion chart engraved on them that shows the decimal equivalent of a fractional measurement. You can see here that the decimal equivalent of 3/8 of an inch is 375 thousandths. This number is obtained by dividing the numerator of the fraction 3 by the denominator, 8. If you divide 3 by 8 on a calculator, you can see the result is 375 thousandths. Some fractions, when converted to decimals, will have too many numbers to the right of the decimal point and must be rounded. Rounding involves the elimination of numbers beyond the required precision of a value. For example, if a value has 6 places to the right of the decimal and only 3 are required on the print, you would round the value to the thousandth place. As you can see, the decimal equivalent of 31/64 is 0.484375. Now, in order to round this value to thousandths, you must eliminate the final 3 numbers. Look at the number to the right of the thousandths place. Only if the number is 5 or greater do you actually change the number to its left. Since the number is less than 5, the number in the thousandths place remains the same for a value of 484 thousandths. If the number to the right of the thousandths place were 5 or greater, the value would have been rounded up to 485 thousandths. The number of thousandths is increased by 1. Most CNC programs are written to 4 decimal places when using the inch system. So in order to round 0.484375 to 4 decimal places, you would look at the number to the right of the 4th place, in this case, the 7. Since 7 is greater than or equal to 5, the number will be rounded up to 0.4844. But what if you needed to round 0.4995 to 3 decimal places? In this case, because of the 5 to the right of the second 9, we would round up and add 1 thousandth to 499 thousandths for a rounded value of 500 thousandths. You must also round numbers when converting metric measurements to inch measurements and vice versa. If you are converting millimeters to inches, divide the number of millimeters by 25.4. If you are converting from centimeters to inches, you would divide by 2.54. Remember, for most CNC programs using the inch system, you would round to 4 decimal places. For example, if 6.55 millimeters needs to be converted to inches, you must divide 6.55 by 25.4. If you use your calculator, you will end up with a result that looks something like this. Rounding this value to 4 decimal places would give you a resulting measurement of 0.2579. Conversely, converting values from inch to metric involves multiplication. To convert from inches to millimeters, multiply by 25.4. To convert from inches to centimeters, multiply by 2.54. For example, to convert 1 inch 856 thousandths to millimeters, multiply 1.856 by 25.4 for a total of 47.1424 millimeters. You would then round this value to 47 millimeters, 142 microns, since most metric CNC programs use only 3 decimal places. Rounding values to the proper number of decimals when tolerances are involved is done differently, however. Tolerance values must always be rounded toward the nominal dimension. For example, let's say we have a value of 12 millimeters 25 hundredths with a tolerance of plus or minus 5 hundredths that needs to be converted to thousandths of an inch. First, find the upper and lower limits. 12 millimeters 25 hundredths plus 5 hundredths gives us an upper limit of 12 millimeters 30 hundredths, and 12 millimeters 25 hundredths minus 5 hundredths gives us a lower limit of 12 millimeters 20 hundredths. Second, divide the nominal dimension by 25.4 to find its equivalent in thousandths of an inch. Use the rounding technique you just learned to round 0.4822834 to 482 thousandths. Now, perform the division problems for the upper and lower limit values. In inches, the upper limit value is 0.484251, and the lower limit value is 0.480314. Here you see the upper and lower tolerance limits. If we follow the normal rules and round the upper limit to 484 thousandths, the rounded value will remain within the original tolerance zone. When you look at the lower limit value, however, rounding the value to 480 thousandths would set the lower limit outside the original intended tolerance zone. Therefore, you would round the value up toward the nominal dimension for a lower limit of 481 thousandths. When you've completed all of the equations and rounding, you will find that the new upper and lower limits fall within the old limits. Part 3. Common errors in performing and expressing calculations. There are several common errors made when calculating values. Learning how to avoid these is a powerful skill. The first thing you must do when making a calculation is to first make a mental estimation of the result. For example, if you need to convert a measurement of 8 millimeters 50 hundredths to inches, first think of the math operation it represents, 8.50 divided by 25.4. Now simplify the equation to 8 divided by 25, and then try to simplify it again into a fraction of which we know the decimal equivalent. We know that 8 is exactly 1/3 of 24, so the result of our mental estimation is somewhere close to 333 thousandths, since we know that this is the decimal equivalent of 1/3. Next, perform the actual equation. After rounding, you can see the value is 335 thousandths. Comparing this to our mental estimation of 333 thousandths, we would record this as an accurate measurement. But what if we had performed the calculation and the result had been nowhere near our estimation? Well, this doesn't necessarily mean our mental estimation is bad. There are a number of mistakes that can be made while performing the actual calculation. One of the most common errors when performing math equations is the transposition of numbers. For example, if the last equation, 8.50 divided by 25.4, was entered into your calculator incorrectly as 5.80 divided by 25.4, our result would have been very different because the 8 and the 5 were transposed. The same effect would be apparent if we divided 8.5 by 52.4, transposing the 2 and the 5. However, if you had transposed the 5 and the 4 in 25.4, the result of the equation would have been close enough to our estimate that it would seem like a valid result. So always take extra care to avoid transposing numbers. You must also read the correct value. Make sure that you read the value using the unit of measurement noted on the print. Be careful. Do not assume that a metric print is noted in millimeters. Check to make sure it doesn't display values in centimeters, and just because you see 3 decimal places on the print doesn't always mean that the values are given in thousandths of an inch. Always check the unit of measure on all prints before calculating values. Another common mistake is inserting values incorrectly into an equation. Multiplying when you should be dividing, or switching the positions of the divisor and dividend in an equation are both examples of incorrectly entering values. Confusion between two people while verbally communicating values is another common error when recording measurements. Therefore, you must understand the proper way to express different values out loud. Let's start with this value, pronounced 2 and 19/32 inches. Values given in fractions are always expressed by saying the number of whole inches, the word and, then the fraction's value followed by the word inches. If the value is less than 1 whole inch, it is expressed by saying the fraction followed by the words of an inch. For example, this measurement is pronounced 49/64 of an inch. When verbally expressing inches in fractions, most machinists omit the words of an inch because only inches are expressed using fractions. Decimals, however, are expressed differently. This value would be stated 3 inches 197 thousandths. Values given in decimals are always expressed by saying the number of whole inches, followed by the word inches, and then the number of thousandths. The words of an inch can be eliminated after the number of thousandths because the unit of measurement has already been stated. The exception to this rule is when the value is less than 1 whole inch. When this is the case, state the number of thousandths followed by the words thousandths of an inch. It is not necessary to say 0 inches when there is no whole inch value. For example, this value is read 640 thousandths of an inch. If your shop utilizes only one system of measurement, it is acceptable to drop the phrase of an inch or of a millimeter when communicating values. Our current example, if stated in a shop that used only the inch system, would be read as 640 thousandths. When expressing inch values to the 10,000ths place, 4 places to the right of the decimal, values are read differently. 10 thousandths are stated immediately after the thousandths are read and are called tenths, because a 10,000ths is 1/10 of a thousandth. This value is stated 2 inches 475 thousandths and 5/10. Always read the number of whole inches, if any, then the number of thousandths, the word and then the number of tenths. Some values may have 5 places to the right of the decimal. The 5th place value is read in tens of millionths and is stated after the tenths. State this value as 816 thousandths, 3/10 and 50 millionths. The 6th place value to the right of the decimal is the millionths place. In the inch system, these are called micro-inches and are typically used only for surface finish measurements, which you will learn about in a later lesson. Metric values are usually stated in millimeters. When values are less than 1 whole millimeter, they can be stated as tenths, hundredths, or thousandths of a millimeter. Values that have only one number on each side of the decimal are stated like inch values with fractions attached to them. For example, this number is read 7 8/10 millimeters. Metric values with more than one number on either side of the decimal are read by stating the number of whole millimeters and then the number of hundredths or thousandths. This value would be stated 15 millimeters, 75 hundredths. This value is stated 225 thousandths of a millimeter. However, it can also be read 225 microns. Part 4. Quality control while measuring parts. There are many factors that will affect a measurement, and if they're not taken into consideration, these variables can substantially modify your resulting measurements. The first factor that must be taken into account is cleanliness. Make sure parts and measurement devices are clean before measuring a feature. Always make sure that the workpiece to be measured is free and clear of dirt and grit. Use a shop cloth or rag to clean any dirty surfaces. Measuring tools must also be kept clean in order to provide accurate readings. This is especially important when using micrometers and calipers because any substance on the measuring surfaces of the device will throw off the measurement. You can see that the contact surface of this micrometer has become rusted due to inadequate care. When fully closed, the reading should be 0, but you can see the micrometer is actually reading just under 1,000. This will cause all measurements taken with this micrometer to be off by nearly 1,000th of an inch. You will learn more about the care and use of micrometers in a later lesson. The second factor that must be taken into consideration when measuring parts is temperature of both the workpiece and the measuring device. Always remember that heat causes material, especially metal, to expand, and conversely, cold causes material to contract. Therefore, workpieces that have been machined recently are probably going to be hot and might need to be allowed to cool before they are measured, or else the measurement taken may be inaccurate. Unless otherwise stated on the print, measurements of workpiece features should be taken at room temperature. Measuring devices are also affected by temperature. Typically, the greater the size of the device, the more subject it is to distortion because of a change in temperature. The next factor that affects measurement is gauge setting and accuracy of the measuring device. Measurement tools are subject to manufacturing tolerances when they're made. They must also be properly calibrated to obtain accurate readings. Many measuring devices require an adjustment tool, such as the one you see here, to return the gauge to the proper calibration. If you suspect your caliper or micrometer is out of adjustment, the calibration must be checked. As you see here, a 1-inch gauge block is being used to calibrate this micrometer. When the adjustment is complete, the measurement of the gauge block should read exactly 0. Calibration of measuring instruments is typically done only by authorized personnel. Check with your supervisor for your shop's policy. The final factor that will affect measurement of machined parts is deformation. Deformation can take place on either the workpiece or the measuring device. Tightening a micrometer too tightly on a thin-walled feature can cause the workpiece to deform, giving an incorrect measurement. Gauge deformation can also occur from tightening a gauge too much around a workpiece feature. You can eliminate both of these problems by using care when engaging the measurement device to the workpiece. For example, make sure the measuring device is properly aligned to the workpiece and use the proper tension when tightening the device to the workpiece. Part 5. The Steel Rule. The steel rule is the simplest measuring device used in the machine tool industry. The steel rule can be laid along flat surfaces in order to obtain a measurement of a feature. Steel rules are graduated in many different ways utilizing both the inch and metric systems, and can have graduations that vary from 1 inch to 1/100th of an inch, or from 1 centimeter to 1/2 millimeter. When measuring along outside lengths and when tolerances are 1/64th of an inch or larger, the measurement can be made with a steel rule. This rule is marked with scales or lines that measure distances anywhere from 1 inch to 1/64th of an inch. There are some inch steel rules that are graduated to 1/100th of an inch, although these rules can be very difficult to read because the graduations are so close together. This steel rule is marked with 2 scales. The smallest unit of measure on the top scale is 1/32nd of an inch, while the bottom scale can be read to 1/64th of an inch. You can also see that there are graduations that will allow you to measure halves, fourths, eighths, and 16ths of an inch. Metric steel rules are typically graduated to 1/2 millimeter. Therefore, this metric steel rule can be used to measure dimensions which have tolerances 1/2 millimeter or larger. This is determined by the specifications and tolerances stated on the print. You select a gauge based on the precision required. For example, this older print calls for a dimension of 1 1/4 inches, so a steel rule would be the appropriate device to use. Steel rules come in many different sizes. They can be as small as 6 inches, or 150 millimeters, and as large as 8 feet, or about 2.5 meters. A dual-dimensioned rule has both inch and metric graduations. Typically, one side measures in inches, and the other side measures in millimeters. There are 3 errors that an operator can make when using the steel rule. 1. The left edge of the rule can be worn. The correct way to use the rule is to align the 1 or any other whole inch mark with the edge of the workpiece. This will give you an accurate starting point from which to base your measurements. If you use this technique, remember to always subtract the amount of whole inches that you start from in your final measurement. On metric steel rules, use the 10 millimeter mark as the starting point for your measurement. Second, the rule must be parallel to the workpiece. Holding the rule at an angle will cause the measurement to appear to be longer than it actually is. The rule must be held parallel to the dimension that is being measured. Third, your eye must be directly over the rule and the piece being measured, or an incorrect reading will result. If your eye is not directly over the scale as shown in view A, you could get a reading which is larger or smaller than the correct measurement. This effect is known as parallax error, which is defined as a change in relative position of an object due to a change in the observer's point of view. In other words, the measurement changes depending on where your eye is when reading the rule, even though the position of the rule and the feature have not changed. You may find it easier to close one eye when taking this type of measurement. Remember, parallax error can occur when looking at either end of the rule. If you place your eye directly above the right edge when reading a measurement, and then check the left or starting edge without repositioning your viewpoint, parallax error will result. In order to eliminate all parallax error, you must position your eye over the start point when laying the rule onto a feature to ensure the left edge of the rule is positioned properly, and then reposition your eye directly over the end of the feature to ensure proper reading of the final measurement. How do you know when your eye is positioned directly over the feature? The solution, as you see here, is to move your eye past the end of the feature you're measuring so that you can see this perpendicular feature. As you move your eye back toward the end of the measured feature, this perpendicular feature will appear to become smaller. The exact point where this feature appears to your eye as only a line indicates that your eye is directly over the end of the measured feature, and this is where you should read the rule. Remember, if you move too far back, the edge of the measured feature will always appear as a line. Move your eye back and forth until you find the proper position. This technique will not work when measuring features that are at angles other than 90 degrees, however. In these cases, use your best judgment when positioning your eye. Check the part print to determine how precise your measurement must be. From this print, we see that the feature must measure 1 3/4 inches plus or minus 1/32. First, convert the nominal dimension from fourths to 32nds of an inch in order to find the upper and lower limits. By multiplying the numerator and denominator by 8, we end up with a result of 1 24/32, which is equal to 1 3/4. Now we are able to determine that the upper limit of the tolerance is 1 25/32, and the lower limit is 1 23/32. Therefore, you can use the edge of the steel rule that is graduated to 32nds of an inch. When reading the measurement, first count the total number of whole inches to the endpoint. You can see from this example that the number of whole inches is 2. Remember, when measuring with a steel rule, to use the 1 inch mark to begin your measurement. Therefore, in actuality, the whole inch measurement would be 1. Now, count the number of graduations from the 2 inch mark to the end of the feature. Since the end of the feature is at the graduation mark labeled 24, and this scale is graduated in 30 the partial inch measurement is 24/32. Add the two measurements together, and the total is 1 24/32 inches. Referring back to the print, the feature is found to be in tolerance. You could also have used the edge of the rule graduated to 64ths of an inch, only this time you would have had to look for the measurement of 1 48/64 inches, which is equal to 1 24/32. When using a steel rule that is graduated to 64ths or hundredths of an inch, it is important that you correctly count the number of graduations when obtaining fractional inch measurements. The graduations are so close together on these rules that it is easy to get inaccurate results. As with all measuring tools, keep the steel rule clean. Do not bend the rule or allow it to rust. This will cause the rule to give inaccurate measurements. This completes your training on the inch and metric systems. See your instructor regarding your next step.